Building permanent infrastructure on the moon requires massive amounts of structural metal. Hauling steel out of Earth's gravity well is an energetic nightmare, meaning we have to source these materials locally. Lunar iron is chemically locked in oxygen, appearing as oxides within minerals like pyroxene and ilmenite. Turning this into structural metal requires reduction at temperatures up to 1600 degrees Celsius, a process that would overwhelm any near-term lunar power grid. Near-Earth asteroids offer an alternative. Many are packed with native metal, pure iron and nickel that is already reduced. The refining energy required to use this material is zero. Traditional asteroid mining requires launching multi-billion-dollar extraction rigs into deep space to process ore in zero gravity. The logistical costs of doing heavy industry in a vacuum make that approach prohibitive for the foreseeable future. The most efficient way to deliver pure metal to the lunar surface is to drop the asteroid directly onto it. The LASSO architecture steers an asteroid into an uncontrolled, unbraked collision with the moon. In this model, fragmentation is the delivery mechanism. The impact shatters the body, distributing pre-reduced metal chunks across the impact site. The resulting crater becomes the mine. Physics imposes a strict limit. If the asteroid hits the moon faster than 7.4 kilometers per second, the kinetic energy instantly melts the metal into useless glass. To make this work, we must identify asteroids on specific trajectories that will naturally crash gently enough for the metal to survive. We begin with the catalog of 42,000 near-Earth asteroids currently tracked by NASA and JPL. The moon's gravity well creates a physical limit. It pulls objects in, setting a minimum arrival speed of 2.42 kilometers per second. When we filter for survival, the catalog collapses. Only 1,124 objects, highlighted here in the blue band, land slowly enough to remain metallic. This reveals a key analytical result. The arrival speed flattens out, dictated by the lunar well rather than the asteroid's approach speed. The orbital geometry that makes an asteroid slow enough to survive is the exact property that makes it energetically cheap to move. We do not need to force an asteroid to be slow. We simply select the ones the solar system has already placed into lazy, co-orbital paths. These asteroids do not offer continuous delivery windows. They present a comb of discrete encounters that only align every few decades. To hit these windows, we apply a nudge decades in advance. A speed change of just centimeters per second accumulates over millions of miles to shift the asteroid's arrival date. The propulsion requirements vary wildly across the portfolio. Targets range from small rocks like 2026 AC4, movable with existing ion thrusters, to 100-meter megaton payloads requiring megawatt-class power. Delivering 1 million tons of metal across the solar system becomes a function of patience and geometric alignment. On paper, the architecture is solved. The orbital mechanics, the specific targets, and the propulsion hardware to deliver thousands of tons of metal exist today. However, the physical filters used to identify these targets create a specific complication. By selecting for slow, Earth-like orbits, we are targeting the exact signature of lunar ejecta, rocks blasted off the moon millions of years ago. Without chemical proof of their origin, we risk spending decades moving worthless lunar dust back to the moon. Telescopes must now gather spectral data on these specific candidates to confirm they are metallic before any mission launches. The LASSO architecture suggests that celestial mechanics can be harnessed as an industrial tool. With enough lead time and the right physics, our future infrastructure is already in orbit, waiting for a nudge.